Okay, Assalamualaikum warahmatullahi wabarakatuh, and very good afternoon to everyone. So, how are you today? Diharap semuanya dalam keadaan sihat walafiat dan sentiasa menjaga SOP untuk to prevent from the COVID disease. So, today we'll continue our lecture in chapter 2, which is signal and noise. So just to recap from the previous chapter, what is signal? Signal is the information that you want to transmit from the transmitter to receiver, the information that you want to share with others. And what is noise? Noise is undesired electrical energy that enters the communications system through the communication media. From transmitter to receiver, and it interferes with the transmitted message, something which is unwanted and can disturb the transmitting signals. So we'll start with knowing about signals. So how signal looks like. Actually, the signal cannot be seen because, as I mentioned in the previous chapter, that signal is a kind of electromagnetic wave, so it can be seen from our very eyes. But actually, the signal can be represented in the form of energy. We can see the signal in can be displayed the signal from oscilloscope. Actually, the signal can be represented in two ways, which are in time domain or in frequency domain. For the time domain, we can display how the signal looks like through the oscilloscope display, while the signal in frequency domain we can see it through the spectrum analyzer. But most people who are interested in analyzing the signals, they normally represent the signal in frequency domain, because there are a lot of information can be extracted from the signal which are represented in frequency domain. So the following slide will show you how the signal looks like in time domain and in frequency domain. So this is the signal which is represented in time domain, and the second figure shows the signal represented in frequency domain. So from the figure you can see that the lambda is about 1 millisecond. So based on the formula of frequency, which is f equal 1 over t. So from here we can know that the frequency for the signal is 1 kilohertz. So when the signal is represented in frequency domain, we can see it is a spike at 1 kilohertz. So in time domain, the x-axis is in time, while the frequency domain, the x-axis in the form of frequency. So you can see the difference between the signal represented in frequency domain and the signal represented in frequency domain. Actually, it is the same signal, but the way it is represented is different. So in frequency domain, we can see that the signal looks like a sinusoidal waveform, while in the frequency domain, we can see only the signal in one spike, which is at 1 kilohertz. So these are the differences when the signal is represented in time domain and when the signal is represented in frequency domain. So now we learn about noise and its effects. So as mentioned briefly in the previous chapters, Noise is something that is unwanted signal, which is corrupts and distorts the desired signal in any way. So noise is very important factor. Why? Because since it is something that we don't want in the systems, so we need to eliminate the noise. So before we eliminate the noise, we need to know about the noise, so that we can eliminate or reduce the effect of the noise to the systems optimally. So based on, as you can see on the slide, that this is the example of noise when it present in the signals. So we can see that the effect of noise will alter the shape of the original signals. So you can see that when noise is added, so the shape, the original shape of the signals will be altered. So it shows that noise is something that's not useful to the system, and it can degrade the quality of transmitting the signals. So as mentioned before, noise is something that can alter the original shape of the signals. It can increase or decrease the amplitude of the signal, and also can delay slightly in time or otherwise corrupted and modified. So from this point, it shows that the noise can affect the amplitude and also the time delay. It means that the effect of the noise can cause the phase of the signal will be changed. Noise is also something which is random. Okay, it means that it cannot be described simply by an equation of a signal value versus time. So maknanya noise ataupun unwanted signal ni something that we cannot form it in the standard equation. So tak ada equation yang can represent the noise. So that's why it is random. So noise ni bermacam-macam bentuk, bermacam-macam frekuensi. So tiada satu definition yang menerangkan noise in a standard way. So it is random. So since the noise is random, so the value of the noise signal at any instant is random too. Okay, so macam kita baling dadu. So the same way it is random. So we don't know the value. There's no specific value of the noise. So the value can be small or can be huge. Noise is not also random in value, it also random in time. Okay, meaning that the frequency, when we talk about time, it shows that the frequency of the noise is random. So it can be a very small frequency, and also can comes in very high frequency. Although the noise is random, but the more we know about the noise and the more we know about its characteristics, we can minimize the effect of the noise to the system. So kalau kita walaupun noise itu suatu yang tidak pasti dari segi value ataupun in terms of frequency, but kalau kita, the more we know, kenal noise itu, apa yang noise hadir dalam satu sistem, dia lagi memudahkan kita untuk minimize the effect of the noise to the system. So since noise is something that can affect the original signals, so it also means that noise can affect the communication system performance in some areas. For example, noise can cause the listener to misunderstand the original signal or be unable to understand it or it at all. So contohnya kalau kadang-kadang kita bercakap dalam telefon, kadang-kadang kita terdengar bunyi-bunyi yang tidak diperlukan, ia akan mengganggu communication dalam perbualan. So noise juga can affect the receiving system to malfunctions. So actually the noise can affect the system. In the receiving system, it will cause the circuitry inside the system will be malfunctions. So when it happens, the system cannot be operated properly. So this figure shows an example of noise when it affects the receiving system. So as you can see here, that when the signal is presented in the system, so it will alter the original. This is the originals, and this is the effect when the noise presented in the system. So it will alter the original signal. So noise can be divided into two categories, which are correlated noise and uncorrelated noise. So what is correlated noise? Correlated noise is the noise when it exists when signal is present. So maksudnya correlated noise is bila ada signal maka wujudlah noise ini. So the second is uncorrelated noise. Uncorrelated noise is present at all time, meaning that whether there is a signal or no signal, so this kind of noise is existed. So kalau ada signal ke tak ada signal ke, noise ini akan wujud berbanding dengan correlated noise, di mana noise jenis ini hanya wujud bila adanya signal. So under the categories of uncorrelated noise, there are two types of noise, which are internal noise and external noise. This diagram shows the whole picture about the category of noise. As I mentioned, there are two types of noise, which are correlated noise and uncorrelated noise. So under the uncorrelated noise, there are two types of noise, which are external noise and internal noise. So under the internal noise, there are three types of internal noise, which are short noise, transient time noise, and thermal noise. And for the external noise, there are 5 types of noise under external noise, which are noise from atmospheric, noise from extraterrestrial, man-made noise, impulse noise, and interference noise. Under the extraterrestrial noise, there are two types of noise, which are solar noise and noise from cosmic. Under the correlated noise, there are only one type of correlated noise, which is non-linear distortions. And under the non-linear distortion, there are two types of noise, which are harmonic distortions and intermodulation distortion. So based from the previous diagram, we know that the uncorrelated noise, there are two categories of noise under uncorrelated noise, which are external noise and internal noise. So in terms of what, when it says external or internals, so for the external noise, it's actually noise generated outside the device or circuits. So when it says internal noise, it means that the noise generated inside the device or the circuit. So for the external noise, there are three primary sources, which are atmospheric, extraterrestrial, and man-made. So for the atmospheric noise, actually it is naturally occurring electrical disturbance originate within Earth's atmosphere. Maksudnya ia berlaku secara semula jadi di atmosphere kita, dan is commonly called static electricity, so ataupun electrostatic. So dia berlaku secara natural. Ia boleh berlaku disebabkan oleh petir ataupun kilat. As we know that lighting is kind of energy. So this energy can spread through wide range of frequency. So since it is energy and signal also a kind of energy, so this energy, the noise energy, can affect the energy in the signals. That's why we call it noise. Okay, but it is insignificant when frequency above 30 megahertz. So for the extraterrestrial noise, it consists of electrical signals that originate from outside Earth's atmosphere and is therefore sometimes called deep space noise. Extraterrestrial noise originates from the Milky Way, other galaxies, and the Sun. Extraterrestrial noise is subdivided into two categories, which are solar noise and cosmic noise. Solar noise is generated directly from the sun's heat. There are two parts to solar noise: a quiet condition, when a relatively constant radiation intensity exists, and high intensity sporadic disturbances caused by sunspot activity and solar flare-ups. The magnitude of the sporadic noise caused by sunspot activity follows a cyclic pattern that repeats every 11 years. Cosmic noise sources are continuously distributed throughout the galaxies. Because the sources of galactic noise are located much farther away from our Sun, their noise intensity is relatively small. Cosmic noise is often called black body noise and is distributed fairly evenly throughout the sky. For the man-made noise is simply noise that produced by mankind. The predominant sources of man-made noise are spark producing mechanisms such as commutators in electrical motors or automobile ignition systems, AC power generating and switching equipments, and also from fluorescent light. Man-made noise is impulsive in nature and contains of a wide range of frequencies that are propagated through space in the same manner as radio waves. Man-made noise is most intense in the more densely populated metropolitan and industrial areas and is therefore sometimes called industrial noise. Maknanya man-made noise ini adalah noise yang wujud disebabkan oleh aktiviti manusia, seperti motor ataupun barang-barangan elektrik juga akan menghasilkan noise. Noise ni dia lagi banyak dalam environment yang ramai ataupun populated metropolitan, di mana biasanya area ini ada banyak kawasan industri dan industri ini banyak menggunakan high voltage devices or circuits. So daripada itu ia akan juga menghasilkan noise. So next is internal noise. Internal noise is electrical interference generated within a device or circuit. There are three primary kinds of internally generated noise, which are short noise, transit time, and thermal noise. For the short noise, it caused by the random arrival of carriers that carries holes and electrons at the output element of an electronic device such as a diode, a field effects transistor, or bipolar transistor. Short noise was first observed by the anode current of a vacuum tube amplifier and was described mathematically by a man called Shotoki in 1918. The current carriers for both AC and DC are not moving in a continuous steady flow, as the distance they travel varies because of their random paths of motion. Short noise is randomly varying in and is superimposed onto any signal present. When it is amplified, short noise sounds similar like metal pellets falling on a tin roof. Short noise, sometimes called transistor noise, and is additive with thermal noise. Next is transit time noise, or TMTTN. To be short, transit time noise is the random noise occurs due to the movement of charge carriers during the transit time. For example, the charge carrier from emitter to the collector of a transistor. When the time it takes for a charge carrier to propagate through a device is significant, the noise becomes noticeable. Then, if transit time delays are excessive at high frequencies, the device may add more noise than amplification of the signals, meaning that this transit time noise is directly proportional to the frequency, hence more significant at high frequencies, meaning that the higher of the frequency, the higher the transit time noise will be. Next is thermal noise. Thermal noise is associated with the rapid and random movement of electrons within the conductor due to thermal agitations. Maksudnya thermal is haba. Bila haba ni, haba adalah kind of energy, and this thermal will affect the electrons. So the electrons will receive more energy than can cause a random movement. Thermal noise is present in all electronic components and communication systems. Because thermal noise is uniformly distributed across the entire electromagnetic frequency spectrum, it is often referred as a white noise. So ia juga dikenali sebagai white noise. Thermal noise is also a form of additive noise, meaning that it cannot be eliminated, and it increases in intensity with the number of devices in a circuit and with the circuit length. So maknanya lagi banyak device, number of device in a circuit, lagi banyak menghasilkan thermal noise. In studying about noise, there are some terms we need to know. First is noise spectral density. So actually it is the noise power per unit of bandwidth. Normally this will be used for signal to ratio calculations. So for the thermal noise density, it can be calculated through this formula, where K is the Boltzmann's constant and T is the receiver system noise temperature in Kelvin. Next term is thermal noise power. So this formula shows how we calculate the thermal noise power. The thermal noise power is represented as Pn, where it is equal to KTB, where K is the Boltzmann constant, B is the bandwidth, and T is the absolute temperature in Kelvin. The next term is noise voltage. So these are the formula how to calculate the noise voltage based from this circuit. This noise voltage is represented by Vn equals 4 times R KTB, where R is the resistance, and K is the Boltzmann, T is the temperature, B is the bandwidth. This is an example of a question how to calculate a thermal noise and how to calculate noise voltage. Let us see this question. Calculate the thermal noise power available from any resistor at room temperature 290 K for a bandwidth of 1 MHz. Calculate also the corresponding noise voltage given R equal to 50 ohm. So it is a straightforward question. First we need to calculate the thermal noise. This is the formula how to calculate the thermal noise. So as I said, it is a straightforward question. Just extract the parameter we need to calculate, then we put in the value in the formula. The most important is you need to memorize this formula and how to use this formula. This example shows of how to calculate thermal noise and noise voltage. So it also a straightforward question. First you need to understand the question and extract the parameter from the question, and then just plug in into the formula. But for the first question, you need to calculate the thermal noise, but you need to present it in dBm unit. So first you need to calculate the thermal noise. So once you get the value for the thermal noise power, you need to transform it into dBm unit. So this is the way how we compute from the original value to the dBm unit. So for the dBm, the important thing is you need to divide it by 1 millimeter. So sorry, 1 milli. This example shows of how to calculate thermal noise when you are given two resistors. So first you need to calculate the thermal noise for each resistor, and the thermal noise when the resistors are in series and also in parallel. And these are the answers for the previous question. So first you need to define or calculate each of the thermal noise for each resistor, and then you need to determine the thermal noise when it is in series and when it is in parallel.